Hello and good day everyone. I'll present our team's work on the Artificial Wallet Sound Zapper, AWaSZ, an autonomous drone aimed at reducing urban noise pollution. The presentation will begin with an introduction, followed by an overview of the system architecture. Then we'll cover four subsystems: power and control, audio and sound processing, image processing, and communication. Finally, we'll discuss cost and scalability before concluding. Let's start off with the problem statement, which highlights three key issues: severe disruption to daily life from Swiftlet sounds, non-compliance with regulations by Swiftlet readers worsen the noise problem, indicating a need of stricter oversight, and lastly, a lack of effective noise mitigation solutions leaves communities unprotected against noise pollution. Addressing these challenges is vital for enhancing the quality life for affected residents. The next steps will involve exploring innovative objectives to tackle these issues. Our objectives focus on innovative solutions for noise pollution from Swiftlets. First, to develop a flying robot for precise navigation around the speakers. Second, to measure sound levels pre and post operation, providing data for real-time analysis. Next, to commit to non-violent, eco-friendly methods for reducing speaker noise. And lastly, to capture real-time video of the loudspeaker area for ongoing assessment. These goals will correlate with the development of a comprehensive system architecture. The AWaSZ combines power and control, audio processing, image processing, and communication within a compact UAV frame featuring a Raspberry Pi 4, USB microphone, camera, and ultrasonic sensors. Key functionalities include navigation to noise sources using localization and onboard sensors. Next, audio classification and noise measurement through SPL calibration and male spectrogram analysis. Next, loudspeaker detection via deep learning with TensorFlow. And lastly, communication with the ground station and mission logging using Raspberry Pi telemetry. Here are the main functions for the power and control subsystem that covers three key aspects. First, power management, which ensures reliable power supply to subsystems, maintaining battery life and preventing downtime. Second, flight control, to maintain a stable flight and execute navigation commands through precise coordination of components. And lastly, subsystem coordination manages communication and operation across subsystems for seamless functionality. Together, these functions enable the drone to operate effectively and fulfill its tasks. Focusing on the block diagram that illustrates interactions within the drone and Raspberry Pi system. The drone system processes inputs through the microcontroller to generate outputs, clarifying the operational chain. The Raspberry Pi system has a similar structure for coordinating functionality. Here is a flowchart to visualize processes and interactions. This chart clarifies the sequence of operations and decision points, illustrating how components are interconnected for efficient task performance. It highlights the pathways for power and information, aiding in identifying areas for improvement. The Raspberry Pi system acts as the brain of the design, handling inputs and outputs. Key components include inputs, such as data from sensors like cameras and microphones to understand the environment. Next, microcontrollers are used to interpret inputs and execute commands for efficient task management. And lastly, outputs to control components such as motors for optimized performance. This integration enables seamless, flexible, and robust operation. The design concept includes key components that enhance the system functionality. Power bank, Raspberry Pi camera, and Raspberry Pi for data capture and processing. Microphone and camera for improved audio and visual data. Li-ion battery for power. Dual camera drone with brushless motors for mobility and stability. And lastly, ultrasonic sensors are used to improve navigation by detecting objects. These elements work together to create a flexible design. Next, focusing on the control features and safety mechanisms. First, obstacle avoidance switch used to detect and avoid obstacle autonomously, ensuring safe navigations. Next, throttle and yaw stick or pitch and roll stick are used to provide precise control for effective maneuverability in any direction. And lastly, emergency stop feature that allows immediate engine shutdown for user safety without sacrificing performance. This feature enhances the drone's functionality and user experience. Moving on, here are two key aspects of drone design. First, the center of gravity, which is calculated at 1.77 centimeters, is stable and within the acceptable range of 1.7 to 3.4 centimeters. And flight time, our energy capacity is 11.1 watt hours with a power consumption of 20 watts, leading to an estimated flight time of 33.3 minutes. Each component, such as the Raspberry Pi and ultrasonic sensors, affects balance and efficiency. Achieving the right balance and maximizing flight time requires precision and planning, guiding our decision in prototype development. Here are the engineering analysis for optimal drone performance, which includes first, power supply. dual system with a 3000 battery for propulsion and a 5000 power bank for processing. Next, propulsion system, ESC regulated brushless motors ensuring smooth flight. Next, control system, pre-installed flight controller with manual override for precise control. Next, center of gravity, CG calculated at 1.77 cm within IEEE stability range. Flight time estimated 33 minutes with current payload meeting operational goals. And lastly, risk mitigation, modular assembly, spare batteries, and vibration management enhance resilience. Moving on to the next subsystem, there are three main functions for the audio and sound processing subsystem, which are first, noise detection. This function uses audio signal processing techniques to identify the noisy, artificially generated Swiftlet sound. Next, noise measurement. Here we measure the noise levels in decibels before and after noise reduction actions. This data is then relayed to the launchpad or base station. And lastly, sound data analysis. In this final function, we analyze the sound data to assess the effectiveness of noise reduction measures. Moving on to the design analysis, the system captures sounds using a USB microphone, saves and converts them into MEL spectrograms for analysis. A CNN model classifies the sound as swiftlet chirps or background noise while measuring decibel levels. If noise is excessive, mitigation measures like enclosing the speaker are applied. The final results indicate the type of sound and noise level post-mitigation, allowing real-time detection, measurement, and reduction of noise. Next is the prototype development for the subsystem. The development has four key stages. First is the audio capture and recording, where the microphone was set up and tested with the record audio Python script to ensure reliable sound input. Second is the spectrogram processing and model training, where audio samples were converted into spectrograms, labeled, and used to train a CNN model to classify sounds as swiftlet chirps or background noises. Third is the real-time integration, where the trained CNN model was integrated into the real-time detection Python script for live sound classification, which was tested in the field. Lastly, the noise measurement and reduction, where the analyzed audio Python script was used to calculate decibels levels and also create audio waveform and frequency spectrum graphs. And a speaker enclosure was designed to reduce noise emissions. The design and analysis of this subsystem rely on key engineering principles. First, advanced signal processing techniques filter and reduce noise, helping to accurately identify swiftlet sounds. Next, triangulation and signal processing locate sources of swiftlet noises for effective targeting. And lastly, sound levels are measured in decibels and noise reduction techniques are applied with their effectiveness evaluated through quantitative measurements. Now, let's explore the image processing functional aspects, starting with real-time video capture, which captures high-definition video of the loudspeaker area and is vital for subsequent processes. Next is object detection, where we use computer vision to accurately identify the loudspeaker, which is crucial for system success. And finally, navigation assistance provides visual feedback on obstacles and targets, ensuring safe navigation. Together, these features enable comprehensive, real-time analysis, paving the way for more technical details. The image processing block diagram includes four main components: input, output, microcontroller, and feedback. The camera provides image and video data, while the ultrasonic sensor supplies distance measurements. The microcontroller processes this data to produce outputs such as real-time video capture, object detection, and navigation assistance, with feedback continuously refining system performance. For software integration, OpenCV handles video capture, VNC Viewer streams live footage to the base station, and YOLO 11 identifies the loudspeaker and obstacles using machine learning. Together, these tools ensure efficient data processing and reliable system performance. The image processing subsystem has two main components: the processing algorithms and the computational power of the Raspberry Pi. The Raspberry Pi 4 acts as the central unit, receiving visual data from the camera and distance input from the ultrasonic sensors. When no object is detected, the drone performs a search pattern. Once detected, the object is classified as either a loudspeaker or an obstacle. If it's a loudspeaker, the drone moves toward it until reaching a preset distance, where the noise reduction process begins. Continuous feedback helps the system adapt to environmental changes. The 64-bit Raspberry Pi OS was installed using the Raspberry Pi Image tool. Essential libraries like NumPy, OpenCV, and YOLO were integrated with Python used to handle image capture, analysis, and object recognition efficiently. Moving on to the prototype development, first is the navigation assistance. The distance measurement feature was implemented to calculate the distance between the flying robot and nearby objects. This function supports object detection and prevents collisions for safe navigation. Using the RPI.GPIO and time libraries, the ultrasonic sensors was integrated through Python programming to provide accurate real-time distance readings. Image processing was prioritized for implementation on the Raspberry Pi microcontroller. The setup involved installing the 64-bit Raspberry Pi OS and essential packages like LibCamera, OpenCV, TensorFlow, and YOLO for various tasks. Initially, the Raspberry Pi camera module did not display video, but troubleshooting revealed that LibCamera was necessary for proper image capture and real-time video recording. Object detection was implemented using a custom YOLO version 11 model with datasets prepared in CV80 and RoboFlow and trained on Google Colab with GPU support. The system successfully detected a loudspeaker, confirming the effectiveness of the image processing subsystem. Last but not least is the communication subsystem function description, which are vital for mission success, focusing on three components. First, data transmission. Real-time video and sound data is sent to the launchpad, ensuring everyone stays informed. Next, control signals. Commands from the launchpad are relayed to the subsystems for real-time adjustments and operational integrity. And lastly, telemetry. Key data like GPS coordinates, battery status, and system health is transmitted for monitoring and smooth operation. These functionalities establish a strong communication and control framework. The drone is equipped with a real-time data transmission system for video and audio streaming during flight. It utilizes a Raspberry Pi 4 with an 8-megapixel camera and microphone to capture media, which is transmitted to the ground control station via a custom Streamlit web interface and Real VNC viewer. Streamlit allows live browser monitoring, while Real VNC enables remote desktop access. A 3DR radio telemetry module at 915 MHz ensures reliable, long-range communication, supporting continuous remote monitoring for autonomous flights. The control signal system enables communication between the ground station and the drone. The FlySky FSI-6X RC transmitter sends commands to the drone's receiver, linked to the R2 Pilot APM 2.8 flight controller, which processes inputs and directs subsystems like motors and navigation. Integrated with Mission Planner software, it allows real-time control and autonomous mission planning. Testing showed accurate command reception and stable drone responses, ensuring reliable flight in dynamic conditions. The telemetry system provides real-time data on the drone's position, battery status, and system health using 3DR radio telemetry through the APM 2.8 flight controller. Mission Planner software displays this data for monitoring. Testing showed reliable updates with GPS issues addressed via calibration and additional antenna, ensuring safety and situational awareness. Here are the key engineering components for data transmission and control. First, data transmission. High bandwidth links ensure reliable real-time video and audio. Second, control signals. APM 2.8 system allows low latency RC control for effective remote commands. Next, telemetry. Offers a real-time GPS, battery, and system health data transmission with minimal interference. And lastly, 3DR telemetry and FSI-6X transmitter. The 3DR uses a 915 MHz module for long-range communication, while the FSI-6X operates at 2.4 GHz for precise control. Our prototype's total market value is about 1,300 ringgit Malaysia, but the actual cost was only 827 ringgit Malaysia thanks to borrowed and owned components. A drone could cover around 0.25 kilometers square per flight, so roughly 400 drones could monitor a 100 kilometer square area. This shows AWaSZ is both low cost and scalable for larger urban deployments. The AWaSZ drone combines subsystems to effectively detect, measure, and reduce urban noise. Experiments showed 87% to 100% classification accuracy and a 12.8 decibel average sound reduction, demonstrating feasibility. It provides a non-violent, low-cost, sustainable solution for noise pollution management. Future enhancement will aim at calibrating sound levels, expanding datasets, and improving autonomous navigation for larger deployments. That is all from me. Thank you for listening.